Hello, everybody. I am John, and this is the first video on the Polymath student channel. So this will be my first physics lecture, and I will be covering basic kinematics. Um, it will be both algebra and calculus based. So I will first do things in the algebraic form, and then I'll put it in calculus. So if you're here, this is my first video. Thanks for watching. So before we can get started on kinematics, we must understand the simple concept of vectors versus scalars. Now, essentially, what the main difference is I think it'd be easier to define scalars, is a scalar has some magnitude. For example, 5 meters. Okay? It's a bit of an odd-looking 5, but it's 5 meters. If I say 5 meters, I don't specify where it is, but you know it's 5 meters. Same way if I said 10 kilograms or 2 seconds. This in and of itself is simply a number and a unit, which means it's only a magnitude. It has no sort of direction to it. You don't know where the 5 meters are, or what the 2 seconds are relative to, or 10 kilograms, but mass will always be a scalar, and so will time, usually. And vectors, however, are different. They are in this sort of directional way. So one vector example is 5 meter to the right, or 5 meters to the left. It's things like this. So if I say something is X meters north, or if something is moving at 6 miles per second, I don't know, I put miles per second to the in the positive direction. And this would be a vector quantity. So scalars are pretty simple, but for the most part, we will be using vectors in a lot of kinematics because it lets us delve into more complicated things such as displacement. So one thing that we need to understand is the difference between displacement and distance traveled. For example, if I go, let's just say that this is x equals 0, this is x equals 10. It's an arbitrary unit. If I go from here to here, then if we measure the distance traveled, we'd see that I went 10 here and 10 here. Therefore, the distance traveled is 10 or 20. I mean, now, if we were to take displacement, which is a vector quantity, unlike distance traveled, which is a scalar, then we would actually find that we've gone 0 meters because we went 10, but then we also went back to our original position. So our displacement is 0. So why is this important? Well, it's important in knowing what we're measuring. There are specific terms that we use for when we're dealing with scalars versus when we're dealing with vectors. For example, I'm sure you've heard the terms speed before. Most people have. So speed, if you're in a car, it'll say like 35 miles per hour. This is purely scalar because it doesn't show you where the 35 miles per hour are. So this is based on distance traveled over time. The vector version of this would be displacement over time. Now, essentially, how we can write this mathematically is delta x over delta t. Delta will usually just mean change. It's a Greek letter, which means change. So what we're essentially saying is change in x or change in position over change in time. This is how you will normally represent it algebraically. If you wanted to write it in a calculus format, then this is simply dx dt. If you're using instantaneous velocity or something like that, then you would need to use dx dt because usually delta t, it'll work for averages and you can make these averages very small, but unless your velocity is completely consistent, it will not give you the instantaneous velocity at some point. But it can depending on the situation, just not always like dx dt will. Now, now that we know that what the difference between a scalar and a vector is, we can move on to defining things like velocity and acceleration. Well, perhaps I misspoke when we said we'd be defining velocity because we've already done that. Velocity is simply change in position over change in time, or dx dt, or delta x, delta t. Now what we're going to do is we're going to be solving for velocity using situations and numbers. So usually physics is a very word problem driven science. It's just mathematical, but the main difficulty of physics doesn't come from the solving the math. Usually it's algebra or simple calculus. The main difficulty comes in setting up an equation that actually models the situation at hand. But usually in kinematics, these situations are fairly simple, especially at the start. So to find our first velocity, we are going to simply assume that I am at position 0 and I go to position, let's say 15. And then I go back to position 7. Okay? So if we find the displacement from this and we treat the right side as positive and the left side as negative, what we can do is we can do plus 15 because we go right 15. And then if you take the jump from 15 to 7, that is 8, simply by doing 15 minus 7, which is 8. So now you have 15 minus 8, and then you get 7. So in total, our displacement from our starting position is only 7. And say I were to do this in a matter of, let's say, 2 seconds. Somehow I'm really fast and I go from this far in only 2 seconds. Okay? So now we know that our displacement is equal to 7 and delta t is equal to 2. Delta t means time elapsed. So if it gives you some time interval, you would say that it's the final time minus the initial. So simply for this situation, we're using that the starting time was 0 and the final time is 2. But if we were to use, say, 12 and 14 seconds instead of, let's say, 0 and 2 seconds, we would still be doing this in 2 seconds. It's just the time interval relatively would be different. But we'd get the same answer. Our displacement is 7 meters and our time is 2 meters. I'm essentially moving at 7 halves, 7 half meters per second. And usually the unit for kinematics will always be meters per second. I think it's easier than the system we have, the imperial system. But this is the unit that you'll normally use, meters per second, for things like velocity. Because if we define this from a dimensional analysis point of view, then we have a length over a time, which is essentially like how fast you're going in that interval of time. Okay. But what if I want to find the speed? Essentially, since the speed they only relies on the amount of distance traveled rather than the displacement, then we could simply add up these two distance traveled. So since I went 15 first, I went 15 meters, and then I went 7 back to position 7, which is 8 meters traveled. So if we want to find the average speed, we do 15 plus 8 because we're essentially treating this as an absolute value, sort of. We're not really taking part direction, simply how much distance we've traveled. And this is 23. The time stays the same. So if I do 23 over 2, then I'll get about, what, 11.5 meters per second as my average speed. So the very next thing we're going to do is we're going to define and solve for acceleration. Acceleration can be simply defined as a change in velocity over some change in time. So mathematically, that would look like delta v over delta t. And in calculus notation, you'll often hear it as the second derivative of x in relation to time. Or if your given velocity is a variable itself, you'll see it as dv dt. So, what acceleration essentially is the rate at which your velocity changes. It is essentially the final velocity minus the initial velocity, which is often written as VO, over some change in time. Let's just say TF minus TO. Because you know that if you are in a car and you step on the gas pedal, you won't instantly reach your final velocity. It'll take a couple of seconds before you get there. That is acceleration, and that's why they usually call it the accelerator in the car. So, how you can solve for acceleration is you can essentially solve for changes in velocity. So, say that I am going 5 meters per second, and then I do this, and then I jump from 5 meters per second to 10 meters per second, and I do this all in an interval of 5 seconds. Okay, and we're starting at just say t equals 0 to t equals 5 for sake of convenience. So by using the formula that we were given here, all we have to do is plug in these numbers as VF, which is 10, V0, which is 5, and then TF is 5, and then T0 is 0. Now we solve this, and then we get 5 over 5, and then we get 1, which essentially means that I am moving at 1 meter per second squared. That is my acceleration. And you can see this because we are moving a meter, and then we are dividing by some time to find velocity, and then we're dividing that by t, so we must also divide this by t. So then you get meters per second squared, or L over t squared by dimensional analysis units. So it's also pretty intuitive. If you just know the final velocity, the initial velocity, and then the change in time, you can usually solve for acceleration just like this. So now that we've defined what displacement is, what velocity is, what acceleration is, and we know what time is, we are going to do our equations, which are very important to kinematics. So there are 5 kinematics formulas that you need to know. The first one is quite simple, and it is the final velocity is equal to the initial velocity plus acceleration times time. And now this is pretty simple. You can kind of get this intuitively from just a simple dimensional analysis kind of thing. Because if you do acceleration times time, then you're essentially doing length over time squared times time, which is equal to L over t, which is another velocity. So it's basically adding two velocities together. And we know that this works because in the situation previously where we solved for acceleration, we were essentially just doing the reverse of this, if you think about it. Because if you want to isolate A, then we get VF minus VO over T, which is exactly what we had earlier. So from using A equals to VF minus VO over T, we can derive this equation, but you can get it intuitively. Normally, you don't have to know the derivations of these equations. um, you can just kind of know what the equations are and you'll be fine. And most things have them like formula sheets, so you don't even need to memorize them. Now, the next formula is displacement is equal to initial velocity times time plus 1/2 AT squared. So again, this works dimensionally because this is length over time times time, which is just length, and then over here we get length over time squared, which is another length. Now, the derivation for this one, it is a bit more complicated than the last one, but it's still pretty simple. So what you essentially know is that if you want to find the average of anything, you add the two groups and then you divide them by two. So if I want to find the average of, let's say, 5 and 6, I add 5 plus 6. I divide that by 2 and I get 5.5, which makes sense. It's in the middle of those things. So if we want to find the, let's just say, average velocity, we can use the initial velocity plus the final velocity and divide it by 2. And that would give you the average velocity. Now, if I want to find what VF is, since we know what the formula for VF is, we can write this as V average as equal to plus VO plus AT over 2. And then from here, I'm just not going to write V average, I'm just going to write this formula. You get 2VO plus AT over 2. And then if you simplify this, you get VO plus AT or 1/2 AT. But the thing is, since we need to solve for displacement, we have to multiply everything by time because right now we would only get a velocity from this, but we're looking for a displacement. So if you multiply everything by time, then you get VOT plus 1/2 AT squared. Also, from a calculus perspective, this formula is nothing but the integral of the initial formula. So if you find the integral of VO plus AT with respect to time, then you would get VOT plus 1/2 AT squared plus some initial x, which would be, let's say x final is equal to x initial. So your plus c constant would be is x initial. And then if you subtract this, then that's how you get the change in x equals to VOT plus 1/2 AT squared. Okay. Next, have another displacement formula. And this is also going to be using the idea of the average velocity, except we are simply going to be accounting for just velocities and time if you're not given acceleration. Essentially, how these formulas work is that in some formulas, you'll get some variable, like you'll get the initial velocity, in some formulas, you won't. So, depending on what information you're given and what you can actually derive, you're going to use different formulas for each situation. So, say that we have a situation in which we're not given the acceleration, but we are given time and we are given the final velocity and the initial velocity, and we need to find the displacement. We have the formula change in x is equal to v plus VO over 2 times t. We already know that this v plus VO over 2 is the average. All we're doing is we're multiplying it by the change in time. So it's essentially average velocity times time. And often on things like graphs, this is how you'll find the displacement of something on a graph. So the fourth and final kinematics formula, or at least the central ones, is going to be VF squared is equal to VO squared. I keep putting this here. Plus 2a change in x. Now, I'm not going to go over the derivation for this one because it is a bit more complicated and you typically don't need to know the derivation. But you can solve for any of the variables listed if you don't have time, as long as you have everything else. So say I want to solve for acceleration and I have final velocity, initial velocity, and change in x, then I can solve for acceleration while rearranging it. So if I relist all the kinematics equations, then we have VF equals to VO plus AT. You can use this when you don't have the change in x, but you want to solve for any of these variables. We have x is equal to VO times change in time. I'll just put it at t, plus 1/2 AT squared. And then we also have x is equal to VF plus VO over 2 times time. This is essentially the average velocity times time. And then we also have VF squared equals to VO squared plus, I don't know why I keep putting it here, plus 2a change in x. So these are the main four kinematics formulas you need to know. Everything else comes from rearranging these formulas. So things that have to do with angles or gravity, well, that is it for today's video. I hope you guys enjoyed it. If you did enjoy, please make sure to like and subscribe. Now that you know all of the kinematics formulas and you know how to, what vectors are, what scalars are, you can probably get through the first, I'd say, a couple of weeks for your physics class. With this knowledge, um, usually this is the first unit covered in physics generally. And as long as you know these things, as long as you know the difference between a vector and a scalar, kinematics is a pretty simple unit. But for our next video, I will be covering graphs, and then I will be covering free fall and other derivations relating to gravity after that. So if you enjoyed, again, make sure to like and subscribe. Otherwise, goodbye.